3 of our webinar series cycle on the topic of the nutrient recycling solutions for primary producers. My name is Dragica Rozdanic, and I am bioeconomy researcher in Munster Technological University. As you can see in the right-hand side corner, there is a QR code which is bringing you directly to our Mainstream Bio page, where you can read more about our Mainstream Bio project. You can see some objectives of our project, and also you can find the registration links for our other webinars. Just to remind you all that today's webinar is going to be recorded. As I mentioned in the beginning, today we are in the golden middle. So we are on the halfway with our webinar cycles. So next week, I would like to remind you all that next week we have a webinar on Tuesday at the same 11 o'clock Central European time on the topic of opportunities for circular bioeconomy to improve the environmental sustainability of primary production. Also, I would like to encourage you all to stay with us on this webinar journey. And you can, as I said, you can straight away, even today, register for these webinars on our main official page. During today's webinar, you are more than welcome, and feel free to ask the questions by putting them into the chat, which is the icon what you can find on your toolbar during the whole webinar. There is no short question or long question, so just feel free to put them in the chat, and they are going to be answered to you by the relevant speaker in the session of Q&A and the panel discussion. Let me say to you something about today's agenda. So we will start with introduction into this interesting world of nutrient recycling solutions. Then we will hear some interesting mainstream bio findings on the nutrient recycling practices, which is going to be presented to us by our esteemed partner, Piotr Skowron from Institute of Soil Science and Plant Cultivation from Poland. Then we will hear some interesting and successful study case examples from Glasport Bio on the topic of innovations to support stabilization and management of slurry, which is going to be presented to us by Stephen Nolan. And also we are going to hear some interesting insights from SeaMeGro on the topic of applications of biostimulants from marine resources in agriculture and horticulture, which is going to be presented to us by Dr. Henry Lyons. After that, we are going to have the panel discussion and Q&A session, where all your questions, we are going to try to answer on all your questions during that time. Also, I would like to encourage you all to, towards the end of the webinar, to refill this questionnaire. You have two options. Use this QR code on your screen, or you can find the link into the chat, already put it down. So, maybe 3 to 4 minutes, but actually it means a lot to us, your valuable feedback. Let me start with this introduction into this world of nutrient recycling solutions. So what actually nutrient recycling solution is, what are opportunities in there, and what's going to look like nutrient recycling solution future. So nutrient recycling solution is a process of reusing essential nutrients in the system, often in the context of agriculture and/or environmental sustainability. Some of the examples of nutrient recycling solutions would be crop rotation, cover cropping, manure management, anaerobic digestion, nutrient capturing and recovering from wastewater, biochar production, and many others, which even Piotr is going to say more about in his presentations. So let me just touch base some of these examples. What is actually crop rotation? So crop rotation is a system already known of growing arable and vegetable crops on arable land, in which crops are alternated in a certain order over a course of several years. The crop rotation includes several agrotechnical and also agroeconomic measures, and it's characterized by temporal and spatial changes in crops and follow. The most common are 3-year crop rotation cycle and also 4-year crop rotation cycle. The most common crops to use are cereals, brassicas, legumes, phacelia, and others. Benefits of crop rotation are improving the soil structure, maintaining organic matter, controlling and reducing the repetition, but also the pressure of disease and the pest, suppressing the weeds, and also helping the retaining nutrients in the soil. The second example is a cover cropping. The term of cover cropping actually implies in a number of different soil measures involving vegetation on the topsoil, with the intention of maintaining or increasing organic matter in the soil, improving the physical and also chemical properties of the soil, promoting microbiological activities in the soil, and reducing the weed pressure due to the higher plant density per square meter. Cover crops also serve the additional function of ground cover, aimed at preventing the soil by water and or wind, and the leaching of nutrients. Primarily, it's more focused on nitrates, thereby mitigating the groundwater pollution. Some of the examples of the cover crops would be amaranth, faba beans, trifolium species, oats, buckwheat, alfalfa, and other legumes. As I mentioned, these advantages of cover cropping would be erosion control, nutrient retention, weed reduction, and building the overall soil health. Let me touch base this manure management topic, which I think Stephen is going to say more about in his presentation. So manure management involves involves various technologies for collection, handling, storage, treatment, and land application, which are based on the size of the herd, soil type, climate, and other factors. Technologies that have been proposed to reduce CH4 emissions include cooling the emissions from manure stored in lagons or tanks, the use of lined and covered manure storage, separating solids from slurry, and by capturing CH4. According to Power, technology alternatives such as filter stripes and concrete pods with retaining walls for stocking manure have been proposed as more economical option for smaller farmers. Benefits of manure management would be including utilizing and reducing animal waste as a resource, reduces environmental pollution caused by animal secretes, and also enhancing the soil fertility. Let me also touch base this very, I would say, hot topic still in the past recent years, and it's anaerobic digestion. Anaerobic digestion is a process through which bacteria break down organic matter, such as animal manure, wastewater, biosolids, and food waste, into the absence of oxygen. Digestion is divided into the 4 phases: hydrolysis, acidogenesis, acetogenesis, and methanogenesis. Anaerobic digestion is used as a part of the process for treating biodegradable waste and the sewage. As a part of an integrated waste management system, anaerobic digestion reduces landfill gas emissions into the atmosphere. So what are the benefits of the anaerobic digestion? So byproduct of anaerobic digestion or actually the loose products are the biogas and the digest. The byproduct from the biogas are the green electricity, heat, vehicle fuel, renewable natural gases, but it's also the byproduct feedstock such as a bioplastic. On the other side, digest, it can be used as organic fertilizer, it can be used for animal bedding, also it can be used as a building material and crop irrigation, but also it can be used as a horticultural product such as plant pots. And let me finishing this introduction by saying something about the future of nutrient recycling solution. So some of the examples on which researchers are currently very focused are on improving the circular economy practices, such as closed loop systems, urban agriculture integration, and vertical farming. Also, improving the innovative waste to resource solutions, such as development of the biotechnology and food waste valorization. Also, in the recent years, there is a big focus on AI and smart farming platforms, such as, for instance, nutrient management platform, but also one of the example is mainstream bio toolkit as well. Resource recovery from wastewater, there is a phosphorus recovery technology and integration of low carbon energy extracting wastewater technologies. As I mentioned it already, our agenda, after this introduction, I would like to welcome our esteemed partner, Piotr Skowron, who is coming from Institute of Soil Science and Plant Cultivation. And he is going to talk more about the mainstream bio findings. I will just stop sharing my screen.
Okay. Hello, everybody.
nutrient practices. I will just say something about your background, Peter, if you don't mind. So Piotr Skoron is a specialist in the field of fertilization, agriculture, environmental protection, and impact of agriculture on the environment. His scientific interests concern the issues of the migration of nutrients from soil to water, the share of agriculture in dispersion of nutrients in the environment, the possibility of reducing environmental pollution, with particular emphasis on agriculture, modern and low-emission fertilizer, and technology of their application, modern laboratory and environmental research methods. He was also a national project manager of the Manure Standards Project from 2018 to 2019, financed by Interreg BSR program. From 2021, he is a project manager of the Organ Safety Project, financed by the National Center for Research and Development, and he is also an expert of the Minister of Agriculture and Rural Development in the international group Helcom Agri. So, dear Piotr, I think you need to unmute yourself. The floor is yours. Thank you so much.
Okay, thank you, Dabi. I try to share my screen. Okay, I hope you see me, you hear me. As Dabi introduced me, I am a researcher from Institute of Soil Science and Plant Cultivation, Department of Plant Nutrition and Fertilization. I would like to show you some findings from my SteamBio project and my point of view at the subject of nutrient recycling. Let's start from the first slide. At the beginning, I'd like to present a few definitions of what nutrient recycling is. It's an overall process where a biomass of nutrient-rich matter is utilized and managed to end back in the cycle of the use of plants. But nutrient recycling practice is the complex of technologies, business models, and more elements. But effect is exactly the same. The final effect is nutrient recycling. We would like to use nutrient-rich material resource for produce fertilizers, to recycle back nutrients into primary production. At the picture you see practice which is connected with manure management, and you see a few technologies here, and you see a few business models here. And this picture presents us that nutrient recycling practice is very complicated sometimes process, and sometimes could be a more simple. And nutrient recycling practice answered for our modern challenges which we have in our agriculture, because food production needs nutrients, and when we need big amount of food, we need a big amount of fertilizers, big amount of nutrients, and of course production and transportation of mineral fertilizers require high amount of energy and fossil fuels, and nutrient recycling could be an answer to decrease this energy and fossil fuels using in the agriculture. And of course we have some limits in our resources. For example, phosphorus is limited and very long renewable. And when we talked about nutrient recycling practices, we have to talk also about bio-based fertilizers and recycled nutrient fertilizers. You can find these definitions in some projects. For example, in most European projects and in European Sustainable Phosphorus platform documents, you can find bio-based fertilizers. This definition is a bit limited because the sources for bio-based fertilizers are various organic waste materials. When we talked about recycled nutrient fertilizers, which we will define in different projects, for example, in synergy projects, we take into consideration in this definition more materials, for example, sewage sludges and industrial byproducts from mining industry, for example. And when we talked about bio-based fertilizers, for example, we have here granulated digestate, ammonium sulfate solution, which is fit into definition to bio-based fertilizers. And for example, when we talked about struvite, we understand that it's fit to recycled nutrient fertilizer. And we see that RNF's definition is a bit wider than BBF's definition. And when we talked about policies, strategies, and common agricultural practice, we see that nutrient recycling is strong support by European Union policy, and we can find nutrient recycling in many European Union regulation, for example, in fertilizing products regulation, when we find that, for example, inorganic and organomineral fertilizers is included to the fertilizing products regulation, new one. We can find some elements in waste framework directive. For example, we can find in Annex 2 to Waste Framework Directive, we can find some processes which we use in nutrient recycling practices. In animal byproduct regulation, we can find the organic fertilizers could be produced from animal byproducts and placed on the market. In water directive, water framework directive, and nitrates directive, which forms an integral part of the water framework directive, we can find many elements of nutrient management and prevent pollution of groundwater, which is strictly connect with recycling of nutrients. European Commission also interest nutrient recycling. This is an example of activities of European Commission. Renew project. It's a proposal of European Commission about starting with new definition for a small group of fertilizers produced from manure, and Commission would like to put it into a separate group where these fertilizers would use not in the limit of 170 kilograms of nitrogen, which limit is for manures, because in this moment every fertilizer produced from manures is under 170 kilograms of nitrogen limit. And in common agricultural policy, we can find many mentions about nutrient recycling and nutrient fertilizers. In common agricultural policy, we have fertilization plan and nutrient management. European Commission tried to promote common tool for nutrient management. I know that this project is abandoned now. It's a fast farm sustainability tool for nutrients. In farm to fork strategy, we can find a European Union integrated nutrient management plan, where we find sustainable nutrient management and rules for market for recovered nutrients. Integrated nutrient management plan is also a part of circular economy action plan, where we find aims like reducing waste, reducing dependence of raw materials, and reducing of greenhouse gas emissions. Nutrient recycling is strong support by Helsinki Convention and Helsinki Commission. HELCOM put first information about nutrient recycling in the Annex 3 to Helsinki Convention. In Part 2, Regulation 2, Plant Nutrition, we can find point 12, nutrient recycling. This is Baltic Sea regional nutrient recycling strategy, where we can find many measures connected with nutrient recycling, and finally we can find Baltic Sea regional nutrient recycling strategy, which should be implemented by HELCOM countries to the 2027. Now I'd like to move to our Mainstream Bio project. As Bert mentioned in the last workshop, last meeting, we have catalog of small-scale bio-based solution here, decision support system, and we have also collection of best practices for improved nutrient recycling. We collect 31 practices. We present it into our tool. I'd like to very fast move to website. Let's try to do. I hope you see our toolkit. In digital toolkit, we have to choose sustainable solution, move to collection of best practice for improved nutrient recycling. When we are here, we see long list of nutrient recycling practices. We can make it more fit for our what we need, what we look. for example, tipping manure. And now we have a further list. For example, when we would like to check anaerobic digestion, we have a short abstract or longer abstract. When we try to go inside anaerobic digestion, we have more details about objective, key elements, practice implementation, legislation, and reference. And as you see, we have very big database about the most popular nutrient recycling practices. Returning to my presentation, we are here again. Okay. I would like to show you two examples of nutrient recycling practices. One is connected with slurry. It's slurry acidification. You can find it here a few technologies, because slurry acidification is a complex of technology. We can use this technology in livestock buildings, reservoirs, and during fertilization process and at the field. And second nutrient recycling practices is, for example, manure or digestage separation. We have many methods for separation. We can manage our manure or digestate to change form of it to more practicable for our purposes. I'd like to present you a few projects. Beside of my SteamBio project, we take part in different projects strictly connect with nutrient recycling. For example, one of our projects is org safety, introduction of an innovative, cheap and environmentally friendly method of hygienization of organic waste. In this project, we develop a method of hygienization of sewage sludge and digestate by special selected plant species like for example, marigold, mustard, buckwheat, or oil radish, and we hygienizated organic waste, and we have finally fertilizers which we can use safely on the field. And second project where we take part like a partner is Synergy, Circular Nutrients for a Sustainable Baltic Sea Region. It's an Interreg project strongly supported by HELCOM. We in this project would like to develop nutrient recycling strategy of HELCOM, and we have many objectives here. So I think that's all. I am on the time. I hope. Thank you for your attention. I'm waiting for your questions, and now I think it's all.
Yes.
Thank you very much.
Thank you so much, Piotr, for your interesting and insightful presentation. And thank you also for sharing our mainstream bio toolkit, so which is just launched very recently. So feel free also to explore that by using the QR code, which I'm going to also share with you later, where you can read more about our mainstream bio project. Now I would like to invite our second esteemed speaker, Stephen Nolan. Stephen Nolan is anaerobic digestion operations and R&D professional with expertise in optimization of AD systems for maximizing renewable natural gas and organic fertilizer production. Since completing his PhD in AD microbiology, Stephen has worked with multiple Irish, European, and UK AD plants to optimize resource utilization, managed green generation through development of the first Irish biomethane to grid project, and troubleshoot various operational crises at the full-scale plants. This work has included several research projects with leading Irish researchers examining various aspects of resource recovery and increasing value and circularity of typically low value or unusable waste fractions. Current work includes mitigation of GHG emissions from agriculture, ongoing AD development and optimization project, utilization of food contaminated plastic, production of high value intermediates project, and downstream the CO2 capture and conversion to usable biomass via microalgae. These methods will increasingly see AD becoming a complete circular bioraffinery model. Dear Stephen, the floor is yours.
Thank you for that long introduction. I will share my screen and just make sure
yes.
it's
and if you can turn your camera on as well. Yeah.
Yeah, my internet is struggling a little bit today, so I think it's safer if I leave it off. But yeah, you can Google me if you need to see what I look like. So I just run through. I have some slides. I'm talking today on behalf of Glasport Bio, which is a Galway-based startup. Started out of the lab of Vincent O'Flaherty in NUIG, or University of Galway, as it's now called. So we'll look at slurry management to reduce greenhouse gas emissions and maximize biomethane potential is the idea. So you might know some of the stats on slurry in Ireland and more broadly in the EU. About 10 or 11% of greenhouse gas emissions from agriculture come from stored slurry. So that slurry sits in a tank, and during storage, it's releasing gas, and then it's downstream either used for anaerobic digestion or it's used as fertilizer. And if you allow the release of gas during storage, you lose some of the value in terms of nitrogen for fertilizer or in terms of carbon for the anaerobic digestion process. So our approach is to tackle the manure storage stage, treat it and reduce emissions, thereby capturing or trapping those nutrients in the system, in the slurry for downstream utilization. It started off in 2018 in a lab looking at rumen fluid, and just happened upon a reaction that was observed, and I just dug into that a little bit more and scaled it up. We saw that slurry methanogenesis in slurry was reduced significantly when treated with this additive. And so we scaled that up through lab scale, 500 mils all the way up to 20 kgs. And more recently, we've scaled it up through cubic meter scale, and then 4 cubic meters, which is the black tank you can see on screen, and then deployment on farms. So I'll go through some of that process, but it is now out on farms being used. As part of that, we containerized a testing lab so that we can essentially lift this container and put it on your farm and come and do analysis and work there. We also, in the background of that container, you can see 200-liter digesters where we can examine the treatment effect on slurry and increase gas production. The IBC scale trial, we had 2 cubic meter tanks filled with 750 liters of pig slurry, and we've done it with dairy slurry as well. Done a single treatment, maintained them at a temperature representing what would happen in a pig shed, and then assessed the results over 30 days. and saw significant reductions in methane production from that pig slurry. So 74% in this instance. That reduction was even higher 3 weeks into the trial, and the effect of the treatment wore off towards the end of it. We similarly tracked methane in those trials, ammonia, and we saw between 40 and 49% reduction in ammonia off-gassing from stored slurry as well. Like I said, we did this with cattle slurry. Also dosed 6 1 cubic meter IBCs filled with 700 kilos roughly of slurry, and we did a weekly low dose treatment, and again saw significant reductions in greenhouse gases, so a 70% reduction in emissions. And then when we tested that slurry downstream, we saw a 70% increase in biomethane production from that same slurry. Like I said, we then deployed it at full scale on a dairy farm in Chinook, which some of the project members here are associated with too, and tracked that and saw that the results we'd observed on lab scale and through pilot scale were repeated on full scale farms. So you can see here the baseline tracked before treatment, and then the application of our additive, and then substantial reduction of greenhouse gases, again, especially in methane. Again, a 78% reduction seen at full scale. This farm has 220 cows and there's about 500 meters cubed of slurry in the slatted tanks. We've gone on and done Vera verification trials. Vera is a gold standard essentially. It's a standard for making sure that the claims you're making are accurate, and so they've these independent trials in the Danish Technical Institute with 5 meter cube tanks filled with 4 meter cubed of slurry, and again have seen the same results. So like I said at the start, the overall concept is reduce greenhouse gas and particularly methane emissions during storage. Leads to enhanced carbon retention in the slurry and then greater biogas potential. We've proven this out in BMPs initially, 500 mils, and then in bench scale reactors, so 10 liter reactors, and scaled that up to 100 liter reactors. And more recently then we applied it to a 270 cube on-farm AD plant in Waterford. So the biogas potential of stored slurry is a function of the slurry composition, storage duration, and storage temperature. And we've observed then that if you can trap the gas in the slurry, the carbon in the slurry, you get an increased methane output. So we've done this with co-digestion of pig slurry with fats, oils, and grease. We had the Kaiserslautern University tested on cattle slurry. They again saw a 38% increase in biogas yield from cattle slurry. And then at the larger scale, we saw a 50% average increase in biogas yield from pig slurry. So yeah, that's the large scale plant. There was an initial even boost in gas beyond what was normally observed as the previous highest. So it was up to 100% more gas, but I'd say there were some operational issues that meant that we achieved a better than normal result in those trials. So on the farm digester study, we manually treated 3 tanks and then fed that slurry into the AD plant. And that's the little AD plant you can see there. Yeah, so our impact on agricultural emissions, if 11% of greenhouse gas emissions from farming are from stored slurry, and we can reduce that by 80%, then that equates to a roughly 7 to 8% reduction in agricultural greenhouse gas emissions, which gets us a long way of the way towards our 25% government target. Yeah, so yeah, as I've said, and then just in summary, there's a significant opportunity there for slurry and manure AD feedstock enhancement. This system we've installed is a simple, automated, low-cost system. And in terms of greenhouse gas abatement and per ton of CO2 equivalent, where aeration costs about €195 per ton, acidification is similar costs. Our treatment comes in at about 58 to 70 euros per ton of CO2 equivalent abated. So that's the Chinook trials in Cork. So thanks to all our funders and colleagues, and I'll hand the floor back to Dragica. Thank you.
Thank you so much, Stephen, for this very interesting presentation. I would like to encourage you all now to use the opportunity also to ask the question to Stephen, as you can find so much interesting information from him. So thank you once again, Stephen. Now we can move forward to our last speaker today, and that's our Dr. Henry Lyles, who obtained his BSc and PhD degree in chemistry from University College Dublin and had over 30 years experience in third-level academic institutions before moving to the private sector to commercialize some R&D work on developing novel products from natural resources. After 8 years as a lecturer in the chemistry in the Dublin Institute of Technology, he returned to Kerry to become the first head of School of Science at the newly established Tralee RTC, which was later known as the Institute of Technology Tralee and now is part of the Munster Technological University. In 1989, he became head of development at the Institute with responsibility for external license with the public and private sector groups in the region, as well as a campus enterprise development. He was the main driving force behind the establishment of the Shannon Applied Biotechnology Center. He took the early retirement option in 2005 to become technical director of Brandon Products Ltd. And in 2017, he became the scientific director of Nutramara Ltd., a new marine biotechnology company, which was set up to manufacture a range of food ingredients and nutraceuticals from marine macroalgae. Henry has had a lifelong interest in natural products derived from marine and terrestrial plants, and has used his background in science to help several coast communities in setting up small enterprise and environmental projects. This has helped in creation of much needed employment in these areas and the development of some innovative products and solutions for sustainable agriculture. Dear Henry, the floor is yours.
Thank you very much, Dragica. I've been mainly talking about marine algae, better known as seaweeds, and SeaMeGro plant biostimulants. I will also, towards the end, mention fish protein hydrolysates, crustacean waste, chitin and chitosan, and make some comments and predictions for the future. Now, I'll start with two interesting slides. Look at this one. You see the current world population. It's gone beyond 6 billion now. By 2050, it should be up to around 9 billion. And the consequences of that for arable land, the world, will be, whereas at the moment we have 2,500 square meters per person, that's going to change down to 1,650 because increased population, climate change, there will be rising global food demand. So that's one challenge. Now, excuse me, as far as fertilizers are concerned, or inputs, there's a different type of challenge. Just spend a minute on this little diagram. The one on the left, the genetic yield potential, that is what you would expect 100% if you have ideal conditions for plant growth. So the nutrients water content, temperature, and so on. If everything were perfect ideal, that's what you get. In practice, we get only about a quarter of that. And the reason for the big loss is down to two types of stress: abiotic stress, that would be drought, salinity, heat, cold, UV radiation, and biotic stresses would be bacteria, fungal pathogens. So that's where the challenge is, to increase the current crop performance under stress. Now, seaweeds or marine algae have been around for a long time. Up to about 70 years ago, we had the traditional uses. They were used as fertilizers, soil conditioners, mainly by island and coastal communities. And note, it was used in fresh bulk quantities. So you're dealing with tons per hectare. And then in the 1950s, liquid seaweed extracts became into play. A totally different situation. The word biostimulant was created some about 20, 30 years ago, perhaps, mainly for seaweed extracts, but also for amino acids, humic acids. Now, the mode of action was a problem for a long time, but it's now there's fairly strong proof that it's oligosaccharides. These are short chain sugar molecules. They act as elicitors or activators of plant growth and disease resistance. And that's mainly what I'll be talking about here. So you're activating the plant's own growth system and its defense mechanisms. There is now a strong scientific basis for understanding the mode of action. That wasn't there up to about 10, 15 years ago. Now, before I get into the plant biostimulants, plant nutrients from the sea in general. Now, in the old usage along coastal communities, you had farmers with horse and carts and later tractors. Potassium is pretty high content in seaweed. Very surprising, because the seawater contains a lot more sodium, but the brown algae especially, they concentrate a lot of potassium. There is some nitrogen, mainly from the protein content. Calcium is there in abundance, not only in seaweed, but also from the fish waste and seashells. Magnesium is got from the sea. Magnesium, of course, used in chlorophyll for photosynthesis. And micronutrients, or trace elements, as they're better known. These have been leached from the land down from the mountains and fertile land into waterways and into the sea. So micronutrients are recycled. But nowadays it's using liquid extracts is the main application for seaweeds in agriculture and horticulture. And note, it's liters per hectare, not tons per hectare. So it's liters per hectare. So the definition of a biostimulant, this came from the European Biostimulant Industry Council a few years ago. It looks a bit complicated, but it's materials that contain substances whose function, when applied to plants or the root zone, is to stimulate. Now note the word, it stimulates natural processes to enhance nutrient uptake, nutrient efficiency, the tolerance to abiotic stress, or crop quality, and it's independent of the nutrient content. So it's not a fertilizer, strictly speaking, but it does stimulate natural processes. And I think this, Pietro mentioned the new EU fertilizer product regulation, which came into effect last July, and marine algae, seaweed, and biostimulants are now part of that. In the past, there were no man's land that could be under pesticides or whatever. So biostimulants are now becoming mainstream inputs in agriculture and horticulture. In the past, you'd have fertilizers, pesticides, and biostimulants somewhere in between. So the benefits, twofold: growth response and then stress defense response. the European fertilizer regulations will mention abiotic stress only, but the biotic stress relief has also been proved, and I think it will probably come under some other heading in future regulations. Now, there are several different types of seaweeds. There are over 500 alone along the Irish coast, but the one that's best known is Ascophyllum nodosum, introduced by Maxicrop in the 50s in the UK. It's very widely used, but it's not the only one by any means. It's a very unique seaweed. It has been highly researched over the past 60 years in the UK, Norway, Canada, Australia, the USA. No, it grows in very extreme conditions, which I will show in a moment. There's the location where SeaMeGro is harvested and processed along the west coast of Ireland. It's intertidal seaweed, so it's exposed not only to the salt water, but to UV radiation, to scorching sun, and very cold weather also. It's underwater for about half the time and exposed to the scorching sun for the rest of the time. Now, how do you convert this fresh seaweed into liquid? So the main process is hydrolysis. You vary temperature, pressure, and so on. There are different variations of this, which I won't have time to go into. Micronization is another one, and cryocrushing. A South African company, Kelpac, have perfected this, and there are also some other enzymes used to a lesser extent, including emerging technologies, but I don't have time to go into those. The advantages are there's no direct toxicity to pathogens or plants. There's no negative effect on plant growth or yield. No problem of resistant pathogens. This is very, very important. The broad spectrum defense is another important point. Unlike most agri-chemicals are very specific, well, here you have a broad spectrum of defense, low application rates, long lasting, and the economics are pretty good. Disadvantages, there was a lot of them in the past. We didn't know what the active ingredients are, you know, unlike, say, if you take a Roundup, we know the formula glyphosate, but there's a number of active ingredients, and it could be synergy between different ingredients in seaweed. A lot of confusion. There are thousands of different seaweeds, is the generic word, but to get uniformity is something the European EBIC are looking at. There were some very extravagant marketing claims made in the past, which were unrealistic. Regulations were slow to change, but we now have the European regulations, and there were plenty of skeptics in the past. So the benefits I've partly mentioned already that come under growth and protection. Site conditioning has been mentioned already by Pietro. Most of the golf courses in Scotland and the west of Ireland were constructed by composting sand and seaweed. And this is a core I took from a local golf course. The challenges for anybody manufacturing are going to be variable composition of raw material, and the actual composition will depend on the species, where it was harvested, the time of the year, and so on.
This shouldn't go on for much more than 5 more minutes, hopefully.
So it's not an easy process. Now, very quickly, fish hydrolysis. Amino acid content is high in fish, so fish waste can be hydrolyzed and broken down to give peptides, oligopeptides, amino acids, which are plant biostimulants. They're on the market in the United States. Yeah, for the future, crustaceans, crab waste, shrimp, and the main products coming out of there will be chitin and chitosan. You'll hear a lot about this in the future. Again, oligo, short chains, very active biostimulants, so from the sea. I think I'm coming up to my time, but alginates, brown seaweeds contain 25% of the dry matter is alginates, a natural glue, which I predict will have a lot of applications in the future. in agriculture and horticulture. These slides I went through pretty quickly. They'll be available to all participants on the website. Future environmental legislation has been mentioned already. Reduction in nutrients of all descriptions, sustainable agriculture. Now, very important, nitrogen metabolism and nutrient utilization. It has been shown that you can use 25% less nitrogen without any losses. So thank you for your attention. That's my email. I'll be glad to answer questions afterwards, or if anybody wants to contact me. Thank you very much.
Thank you, Henry. Thank you so much for sharing with us your knowledge today. And now I would like to ask all our speakers to turn their cameras on. If you don't mind, thank you. And now we are coming to the section of Q&A and panel discussion. There is some interesting questions raised during your presentations. So I would like to start with asking the question. Before that one, can I, Henry, ask you also to put your email into the chat, please? So yeah, I would like to ask Stephen the question for you from Emmanuel. Firstly, he said, thank you for the presentation. Please, can you elucidate on how to determine GHG reduction during AD process? That's the first question for you, then we can go to another one.
Sure. So there are two separate things. So you're doing the greenhouse gas reduction piece during slurry storage to then get more gas out of that slurry during the AD process. So you treat the slurry, and then you validate what you're doing with odor monitoring and air monitoring and off-gassing monitoring systems. And then you use that treated slurry in the AD system, and most plants would have a baseline that they're familiar with of what they normally produce. If they feed the same amount of slurry in, they should receive more gas being produced from that same slurry input. That makes sense.
Okay, thank you. And also there was the question, what is the current strategy for efficient biomethane recovery from AD process?
Efficient biomethane recovery from AD process. So typically there will be a CHP on site, and the biogas is burned to produce electricity. That's historically what was done. There's a big shift towards biomethane capture. So there's a number of different approaches to capture that biomethane, separate out the CO2, amine scrubbers or membrane scrubbers or pressure swing absorption. The kind of critical point in Ireland at the moment is that there's only one grid injection point. And so when you do take that biomethane out of the AD system, there's nowhere to go with it essentially. So some of the work that James is doing is looking at refining grass and getting some of the higher value stuff from the grass first, and then on the back end digesting the leftovers. And in that kind of system, you could use the gas produced to run the system, if that makes sense, so that you're not dependent on a grid injection point, and you have this kind of circular sustainable system that's able to power itself. So there's a few different approaches that could be used. It just is context specific, and some of the bigger plants will develop out grid injection points as well, but right now there's not much options there.
Thank you so much for your answer, Stephen, as usual. And now one question for you, Henry. Can you tell me what specific benefits do biostimulants offer to agriculture producers in the term of improving the crop yields and also in reducing the needs for using the standard conventional fertilizers?
Yeah, I could go on for half an hour to answer all of that, but basically, biostimulants are very useful when a crop is under stress for any reason. So it can be too much water, very little water, drought, excess temperature, or frost. So it is stress of all descriptions, extremes. If conditions are ideal, the effect is much less. And on the biotic, now at the moment, some of the seaweed extracts do not mention the effect on bacterial or fungal pathogens, but it has been shown beyond doubt that you can reduce the amount of agrochemicals required. This has been done scientifically in recent years. It's not a total replacement, but it may be that a combination of different biostimulants would give a very high efficiency rate, close enough to what agrochemicals will do. A lot of companies, some of the major chemical companies are now picking up these biostimulants and doing their own work on them as well. So it's the whole wide range of growth and protection.
Oh, thank you so much for your answer. Do you know, by any chance, some of the most recent innovative products which came from marine?
The innovative products from the marine, chitosan, I think. Chitin is the second most abundant polymer on the Earth's surface. It comes after cellulose on the land. Of course, it's made up of units of glucosamine, the amino derivative of the glucose. It is used in the Far East quite a lot, has a myriad of applications. I think that will be, that's the one I would put my money on if I were betting for the future. I'm a little bit rushed at the end, but the idea of alginate, a natural glue, natural polymer to use in food products, I can see that having a bigger utilization for seed treatment, coating, slow release fertilizers, erosion prevention, mulching, and so on. We've come up with a method. Alginate can be very expensive. You might say the economics will be all wrong, but we've come up with a method of releasing the alginate from the seaweed without going through the expensive process. But that's for another day. We're working on it.
That's perfect. Thank you so much for sharing that with us. And now the question for you, Piotr. What are some key challenges and considerations in implementing nutrient recycling practices for, let's say, smaller scale producer, and how they can be addressed? If you can unmute yourself, we cannot hear you.
Yeah. Do you hear me? Yeah. Okay.
Yes.
It's a very hard to shortly answer for this question because challenges that depends about condition. When we talked about farms, about farmers' activities, we have to see all screen of it. For example, financial status, biomass availability, technology availability, and everything depends about what farmer have to choose. For example, when a big amount of biomass is available in the locally, for example, and the biogas plant is available, the reasonable direction will be put, for example, slurry into biogas plant and use digestate like a fertilizer. when we have no biogas plant, for example, second option is slurry separation, where we will have, for example, two separated parts of slurry with different content of nutrients, and in this way, nutrient management will be easier when in this situation. Very important thing is that farmers should see benefits from nutrient management, nutrient recycling, and farmers should feel support from regulations, support from common agricultural practice, and what else? And one thing is is on our side, scientists and advisors. We have to work for increasing knowledge, increasing awareness, increasing recognition of nutrient recycling practice in our agriculture, locally and nationally level. I hope it's an answer for this question.
Mm-hmm. Okay, thank you. Just shortly want to ask you as well. If I would be a small primary producer, farmer, what would be kind of your recommendation for most effective and the practical nutrient recycling practice, what I can easily adopt?
The first step should be always nutrient management and nutrient and fertilization recommendation. When we know what we have and how we would manage it, it's a beginning of process. Second thing is check availability of technologies, because very important is technology readiness of technology, because when we have introduced, for example, some practices in our area, very easy to, in cooperation with advisors and local policy makers to introduce something in the farm. So very often is implemented, for example, slurry acidification. So cost is significantly high, but slurry separation is very popular. Anaerobic digestion is very popular, and we have many very good quality fertilizers from anaerobic digestion. So it's all.
Mm-hmm. Thank you so much for that. I was just thinking from the perspective, what can be, it's always a challenge, to adopt a new technology. So I was just wondering what would be your recommendation on that one. And just for the end, I would like to also ask you, Stephen, as you are working on that, like, what would you recommend, as like from your experience up to now, for, let's say, for a smaller farmer, what would be kind of, it's basically the same question. What would be the easiest technology to adopt?
Slurry separation and sending the solids to AD with the Glasport additive to stop greenhouse gas emissions in the first place. I think that's the most straightforward. Instead of 15 cubes per ton of slurry, you're looking at maybe 120 cubes per ton. So the methane potential is a lot higher from the solid fraction, and a good amount of the nutrients are retained in the liquor, so they can be recycled to the farm. The problem most people have is that if they're in irrigation, which a lot of farms are, then they can't receive those nutrients back onto the farm as digested at the moment, the way it's set up. So there's some work to do in terms of digestive processing to have essentially a biofertilizer equivalent to chemical fertilizer that can be applied to land higher than the 170 kilos nitrogen per hectare. But yeah, slurry separation is the starting point. It's the easiest one. It's the low-hanging fruit, and we should be trying to do that and ship the solids to the existing digesters and new digesters as they come on stream. Thank you.
Mm-hmm. Thank you so much for your answer. And I would like to use the opportunity to thank you all speakers for being today with us. I really appreciate that one. Also, I would like to thank to all attendees today. I'm going to send you an email with the YouTube link, just in case if you want to rewatch the webinar today, and if you want to, by any chance, share it maybe with some of your colleagues. I would like to just also use this opportunity once again to ask you to refill our questionnaire because your really feedback means a lot to us. And also, I would like to use the opportunity to, invite you again to our next webinar, which is going to happen next Tuesday at the same time at 11 Central European Time. You can use this QR code on your screens, which is going to bring you straight away to our Ministry Bio page, where you can find the registration links to our webinars. Once again, thank you all for coming and being with us today. And I look forward to seeing you all next Tuesday. Have a great day, everybody. Bye.
Thank you.
Bye.
See you. Bye.
Goodbye.
Thanks, Gordon.
See you. Bye. Did you stop recording? No. Okay, maybe I can do it.